This new video will explore the mathematics of the graphic static solution where we found the peak force to be 1,900 pounds roughly. You could also see it with the number peak force 1,900 pounds. That was done graphically. Let's do this with SAP, finite element program, but let's do it in a kind of an easy breezy manner. So not graphic statics, just something fast. File, new model. Make sure that you are in the units that you want to be. You cannot change this later. You can display things differently later, but if you say 75 feet and you display it as inches, it will just be 75 times 12. So I'm going to do a grid here. I'm just going to do two grid lines in the x direction at 75 feet because that was my distance. In and out of the plane of the screen will be one grid line, and then two grid lines in the z. Get used to having z going up, and I think it was 20.2, but that doesn't really matter. Close the 3D view and hit XZ on our view. It's a two-dimensional view. I'm going to put in a dot here, which is just a joint or a node, right here at the left side and right here on the right side. You could always go in and change these later. I'll show you what I mean by change. If I just drop a dot here for the crown, I missed my 20.2, but I will touch that crown and right click and then go to location, and I can place it right in the middle here by double clicking that. 37.5, and the crown was 20.2 on the rise. Okay, I can hide the grid. View, show grid. And before we hide the axes, I just remind you that the z-axis is going up in SAP. This is just a target here. We don't really need this point, but I'm going to just show you, I want you to notice where this one is. The next thing I'm going to do is draw an element, and you could do it with this left quick draw icon, which looks like a little stick, or you can go draw frame cable tendon. And we are going to do this in a really simplified manner. Instead of the default is straight frame, but drop down to curved frame and pick the left point and pick the right point, and it tells you, you could see it right here, that our Cartesian coordinates of the left and the right are known, but the third point is not defined yet. So we said that was at 37.5 and 20.2. I'm going to actually get rid of that predefined point here so that you see, that what SAP generated was a series of piecewise linear elements that passed right through that point. The next thing I wanted you to do is to notice that is one entity right now. It's one element. So I'm going to delete that, and I'm going to draw that and break it up into multiple elements. So left side, right side. There's my crown, 37.5 and 20.2 on the Z. But notice that I had this as a single object, and now I want to break this up into multiple objects. You could do as many as you want. 10 is plenty here, so that's the default. Hit OK. And now we see that it's broken up into a series of nodes, and with nodes and differentiating the elements. There are 1, 2, 3, 4, 5, 6, 7, 8, 9 such nodes. So I will go to my GeoGebra window and look at weight over 9 over here. Weight over 9. And weight over 9 was 308.18. So let's remember that number here. The next thing I want to do is define a load pattern. The default is dead, and the default is modal, but we want something other than dead. and I'll explain why later. So just use other as the type, and notice that the self-weight multiplier became 0. Don't hit OK. Use the add button to get the drop down. That's very, very common in all of these SAP applications. And I will touch these nodes that have to be loaded. This isn't perfectly correct because what we did was we put the load at the midpoint of these segments in GeoGebra, but it's okay. We're just estimating here. And then assign joint loads forces, and we will choose my load, and it was 308.18 pounds, and it's minus because it's going down. Okay, we're almost done. We just have to secure this point and this point. We'll just make them pinned right now. They could be fixed, they could be pinned, but let's just make them pinned. Assign, touch them first, assign joint restraints and make them pinned. And now we're ready to roll here. Analyze, run analysis. We're going to turn off the dead, the built-in dead, turn off the modal, and run, and it will ask us to save. So I'm going to say, call it some kind of test. But before you do that, make sure you make a subdirectory called SAP or SAP runs or SAP analyses, because it makes about 20 or 30 files. You don't want to clutter up your directories. So just make a subdirectory where you're going to put your SAP runs in there. And what will happen is that we will get forces starting the, you could see that it's pinned here. It's coming down. Looks like we have some bending in here. So let's take a look at the bending. Show the forces in, show the forces display, show forces in the frames, the moment. Let's just do it as a diagram here. And you can see that I have a little bit of positive moment, a little bit of negative moment. I just made this a parabola. It's not a perfect funicular. Let's look, nevertheless, at the axial forces now. The axial forces just as a fill-in. The axial forces are growing and growing as we move down. And ta-da, look at that number, 1874. 1874 is my axial force. And remember what we had here, 1899. So even with this approximation where we had some bending, you're going to do better than that. You will have less bending than I did in this very, very quick analysis. But I would like you to see how the truth is that the graphic statics is perfectly funicular, zero bending, and even with this little bit of bending, we had excellent agreement. Thank you.